Okay, so I'm going to look at a second hypothesis question on June 2023 Edexcel's Stats A-level paper. And it's question 4 of that paper. So this one is about hypothesis testing on a sample mean, where you have a little bit of a nuance on this. So, question goes, it was about heights of adult men in 2 regions of a country, region A and region B. And the first one, it says, it was found that the heights were normally distributed with a mean of 175.4 and standard deviation of 6.8. So if we say let X be height of men in region A, we've got X being normally distributed, it tells us it is, mean of 175.4 and a standard deviation of 6.8. So when you write in the standard deviation, for the normal, you always put the standard deviation squared, you put a variance in. Anyway, so 6.8 squared there, this square, keep it in mind. Right, so the first question says, find the proportion of these men that are taller than 180. Now, really, all they're just doing there is saying the same as you would, I select a man at random. What's the probability that they are above 180? It's just basically saying what kind of fraction or decimal or percentage or whatever are greater than 180. So really, what we're trying to find is the probability that a random person is above 180. That's what we're doing. I think the wording might have thrown a few people. It's only a 1 marker, so it's just a calculator job. We're putting 175.4 and 6.8 into our calculator. We are doing cumulative. It doesn't matter that whether you put an equal to here or not. Normal distribution is continuous. So technically, the probability that X is dead on 180 is 0. You talk about regions, you talk about areas under the graph. And so therefore the area dead under 180 is 0 because it has 0 width. You would talk about it for 180, you talk between 179.5 and 185. You can look at that range, but technically dead on 180 is 0. So you don't actually need to have an equal to here. You can put an equal to, they're not going to penalise you at all. So we're just looking at property of X is greater than 180, stick it in your calculator. It's a 1 marker and apparently you get 0.24937. And they accept anything up which rounds to 0.249. Okay, so pretty okay starter. Just the wording was a little bit ropey. Hopefully you realised it's the same as probability, that we're looking for the proportion of men there. Now comes the hypothesis test. So we have a student claiming the mean height of adult men from region B of the country was different from the mean height of adult men from region A. They took a random sample of 52 adult men from B and they had a mean height of 177.2. Okay, so what we're going to look at, we're going to test at the 5% level, hypothesis test. We're going to test that student's claim. So the student's claim thinks it's different. Now that's quite important. They're not saying it's taller or they're not saying it's smaller. They're saying it's different. So it's a 2-tailed test. We're going to be considering both ends in some ways. So should we say for part B, let Y be the height of men region B. Okay. So the student is assuming that the standard deviation of the heights of men in both regions is the same. So that 6.8 is going to hold. But what they are saying is they think that 175.4 is different. Now, if they've taken 52, a sample of 52, and they got a mean of, what did they get a mean of? 177.2. it's easy to go, oh, that's higher, that average is higher. So aren't we just looking at whether they are tall or not? But they specifically said that it's different. So actually we don't just focus on the fact that it's taller, we actually realise it's a two-tailed test, which is testing whether it's different. So we've got to state our hypothesis clearly. Again, that's just going to give us a mark straight away. So it's a mean. They've taken 52 people. We're not looking at one individual person and saying, whoa, they were 177.2. What's the likelihood of that happening? We've taken 52 of them. Some of them will be shorter than 100, some of them will be taller, and we've averaged out their heights to get 177.2. So that standard deviation gets changed because of that. The bigger your sample is, the more likely your average should be close to what it should be. So if 175.4 is correct, it should be pretty close to 175.4. The 6.8, no, that's just for one person. We're talking an average of 52 people. You know, if you can imagine that was like 5,000 people and that was true, it's still 175.4. You would expect it to be pretty darn close to 175.4, virtually dead on. So the bigger your sample you're taking, the more your standard deviation should come in and get smaller and smaller and smaller. It should be closer and closer and closer to this 175.4. So what we do for a mean is we're taking the mean now of that sample. So we use y bar because it's the mean of a sample that we're taking. And that should be normally distributed. 174.4 is what we are going to assume it is, but I'm just going to put mu in here, our mean, and our standard deviation for our sample is going to be 6.8 squared, and we divide by the sample size. So we're taking a sample of 52, so we're going to divide by that 52. Our null hypothesis is going to be that mean is just the same as A, no change. So it's going to be that the mu is 175.4. Our alternate hypothesis, H1, is going to be that it's not 175.4. I know we got an answer that was bigger, but we're testing, he just says that it's different. So we don't look at we don't consider the situation that it's actually bigger, because he's just saying it's different. Let me just get the question back up on here a minute. Won't be a second. Slickly done, never mind. Right, so we're testing that it's just different, so 175.4. Now I know we're getting a result that's much bigger. So we are going to be testing whether we get this result or worse than it. Well, surely worse than 177.2 if 175.4 is correct. Worse than 177.2 would be anything bigger than 177.2. So we are going to find the probability that this y bar is greater than or equal to, if you like, 177.2. So we're putting in our calculator mean of 175.4, because we're going to assume it hasn't changed. We're going to assume that null hypothesis is correct. Standard deviation, though, we're going to be putting the square root of this. So that's 6.8 over the square root of 52 when you square root it, because you are basically square rooting 6.8 squared over 52, which is obviously 6.8 over root 52. So that's your standard deviation you're going to be putting in your calculator. So mean of 175.4, standard deviation of that. And we're looking for greater than 177.2, so we're looking for the right-hand side, 177.2. Put it in your calculator. Out comes, according to this, 0.02814. So that's roughly 2.8%. So the likelihood of getting that result is 2.8%. And if this was a one-tailed test, and we are testing at the 5% level, it tells us, we would be going, oh wow, that's too small. Not good enough, because we need it to be above 5%. However, 2.8% in this case is not going to reject H0, and the reason being it's a two-tailed test. So that 5%, we're going to be looking at 2.5% either end. Now I know our result is greater than. Our result is that this average is actually bigger than 175.4. But we can't just concentrate on the one side because we're talking about a two-tailed test. We're just looking at this student's claim. So we just look at that side and go, well, 2.8%, unfortunately, it's close, but it's not close enough. It's not above that 2.5% we've got allocated to the greater than side. So we're going to say 2.8% is actually greater than 2.5%. So therefore, even though that's small, it's not small enough for us to reject H0. So we do not reject H0. And as usual, we've got to put that claim in some kind of perspective. So we need to say there's insufficient evidence to suggest region B's heights are different. Oh, I can't just squeeze that in, but hopefully you heard that okay. So, it's a close one. The 2.8%, really close to the 2.5% cutoff. And I think a lot of people would look to the 5% and go, oh, it's lower than 5%, but it's a two-tailed test. So, we're not going to be rejecting that naught. We're going to say H0, we're going to say that actually region B, it looks like from our sample, actually we're sticking with 175.4. There's no difference between them. Okay, now there's a part C on this for 1 mark. And the part C is find the p-value for the test in part B. Now the p-value is basically this idea that we always test, there's our significance level, that's our cutoff, 5%. But we never get dead on 2.5%. Our values that we get are never exactly 5% or below 5% or whatever, 1% or whatever significance level is. So our p-value is basically this number here. Now, this number here, our 2.8%, is actually, though, for our two-tailed test. So we've got to double that, because don't forget, we split our 5% into 2, because it's a two-tailed test, and compared against 2.5%. So actually, our p-value for this whole test, a two-tailed test, will be 2.8% doubled. 2.8% times 2. So our part C, just a 1 marker, our part C is that our p-value is 2 times 2.8%, or 5.6%, or 0.056. Okay? So it's the actual probability that your result is giving you, rather than the actual significance level. That's your p-value. Okay? Hope that's okay.